Welcome back to part two of this lesson on the carbon cycle. We're looking at the comparison between the input of um, human generated carbon gases with those from natural sources. This particular uh, diagram shows the relative scale of uh, total human emissions compared with aviation uh, within a year, and also then showing us some volcanoes. So you can see, for example, the effect of the Eyjafjallajökull eruption back in 2011 that put 150,000 tons of carbon dioxide into the atmosphere, and how that compared, and how that was a small but reasonably significant contribution to about the 500,000,000 tons of CO2 that volcanoes typically put into the atmosphere in a year. If we compare that then with uh, aviation, we can see that all worldwide volcanoes are a significantly lower source of CO2 even than just aviation. If we compare that with total global emissions, it's much, much more. If we do the sum, what we see, if we divide the total global emissions by volcanic emissions within a year, we can see that it's actually 167 times greater human emissions than volcanoes. Nathan Gill was 167 times wrong. Human emissions clearly have the biggest source of CO2 currently going into the atmosphere. If we look at the effect even of big volcanic eruptions on this graph, here we've got these three uh, massive volcanic eruptions, some of the biggest ones from the end of the 20th century, and the record of CO2 from Mauna Loa in Hawaii. Remember, the atmosphere is a global common. It's shared. Okay, we have one atmosphere. So volcanic activity in one place may well be detected elsewhere in the atmosphere. But if we look at this graph, we can see, despite these big spikes of CO2 from these big eruptions, they haven't had an effect on the CO2 graph. We can't see a noticeable impact, which shows that the human input is of a scale bigger, two orders, nearly three orders of magnitude bigger than what we see even from the big volcanoes. This is the Mauna Loa Observatory. If we think about why we measure CO2 on top of this place, it the answer is really it's one of the most remote places in the world. We can get a good measure of global CO2 from a place that really has no industry around it. There aren't significant sources of pollution immediately around this observatory. It's it's getting a good global average. I mean, there are other places where we could find the same sort of thing. For example, Antarctica. But this is the place that we tend to use as our reference because it's not going to be affected really by much in the way of local factors. If we plot the change in global fossil carbon emissions, so our use of fossil fuels and also you see here cement, you can see how the exponential rise, particularly in the second half of the 20th century. We see different fuels changing. Notice how coal uh, has becoming less of a thing. If we saw the next 20 years of this graph, I suspect you would see that going down a bit as well, despite what's happening in China. The use of natural gas increasing rapidly through the second half of the 20th century. But this is a lot of um, gas going into the atmosphere. The need for an energy transition is fairly clear from this. However, as we know as geologists, that energy transition won't be straightforward and will require a huge amount of mining activity to give us the metals we need if we're going to electrify our energy. So, as we see the sunset over the Mauna Loa Observatory, make sure that you've completed questions 6 and 7. This is also a good time to revisit what's in a word. How many of those definitions now can we refine? How many definitions do we have that we can use to move from an I don't know to actually understanding these ideas? If you've got any questions, ask me next time you see me in class. I'll see you then.